Welcome back, students. Today we're going to be talking about linear functions. A linear function is going to be an equation that's written in the form y equals mx plus b. Y and x are going to be our variables. M and b are constants, meaning they're just going to be some numbers. The graph of a linear equation is a line, hence linear. Likewise, a linear function is a function whose graph is a non-vertical line. Non-vertical meaning straight up and down. It can't be straight up and down. The reason for that is, just like we saw from the last lesson, you cannot, it has to pass the vertical line test. Whereas if our function had a vertical line, it definitely would not be passing that test. A linear function has a constant rate of change and can be a linear equation in two variables. Okay, so linear function has a constant rate of change. That is going to be very important. A nonlinear function does not have a constant rate of change, so its graph is not a line. So what makes a constant rate of change? If you imagine a line in your head, okay, that line has a certain steepness. It might be very steep, meaning it's going upwards very quickly. It might be not as steep, so it's not rising as quickly. That steepness that the line has, that's the rate of change. Okay. All right, so we're going to identify if these are linear functions or not linear functions. Right here, it forms a line. This graph is a linear function. This one does not form a line. It is not a linear function, so nonlinear. All right, identifying linear functions using table. Now with graphs, you can see that's kind of easy. Tables get a little bit more complex because with the graph, we can see the rate of change. Just visually, I see this always had the same steepness. Therefore, the rate of change was constant. This one's going down, so it has a negative rate of change. Then it flattens out, so it had no rate of change right there. The rate of change was 0. And then it's going up. Now it's got a positive rate of change. The fact that this doesn't form a straight line is a visual way of us seeing the rate of change was not constant. Here, we need to be able to check on the rate of change using another method. The way we're going to calculate the rate of change is the same way you'd calculate slope. So we need to figure out the rise and the run. Now, y is the value that rises, x is the value that runs. So we see this goes down 6 and then forward 3. That would create a slope of -2. So you always put the change in the y value over the change in the x value. Now, we care about it being constant. Okay, so we need to check to make sure that it maintains that exact same slope in other parts. Right there, we went down 6, forward 3, down 6, forward 3. Everywhere we maintained that exact same slope of a -6/3, which is -2. Now, in this case, it used the same numbers each time. It doesn't always have to have the exact same numbers. If the very next change took us down 12 and forward 6, well, that would be a -12/6, which would still give us a -2. So even if your numbers change, these numbers that I have in blue and red, that's still okay. What's important is the fraction, that the fraction always remain the same. In this case, it did. So table 1 is linear because it has a constant rate. All right, table 2. We're going to check on the slope. So we find the change in y and the change in x. So 7/2, 11/2, and 15/2. Those three fractions are not equal. Therefore, the rate of change changed. So it's nonlinear. It does not have a constant rate of change. Okay, so now using the equations. Remember from before, it said that a linear function could be in the form of y is equal to mx plus b. So in all the equations we look at, we're seeing, does it fit the form y equals mx plus b? And it doesn't have to look like that exactly. What we're really asking is, can we change it to that form at very least? So looking at this equation, yes, we got a y right there. Notice we're missing an mx, anything for mx. That's not quite as worrisome because I could rewrite this same equation in this form where it's a 0x plus a 3.8. Okay, 0 times x is just 0. 0 plus 3.8 would be 3.8. Both of these are the same equation, just I was able to rewrite it in a y equals mx plus b format. Therefore, it must be linear. The rate of change is 0, and the y-intercept is a 3.8. All right, now in this one, I do have an x. In the mx plus b format, it doesn't have a square root, so I'd need to get rid of the square root. So I could try to square both sides, but if I square both sides, then I'll have a y squared, which we shouldn't have a y squared. There's just no way of dealing with that square root in a way that allows me to get it exactly like y equals mx plus b. So this one is nonlinear. Okay? Over here, x is in the denominator. So in order to get it out of the denominator, I could multiply by x, but then I've got it as x times y. Well, that's not the way this is formatted, so this one is also nonlinear. All right, this one, it's not quite in mx plus b format, so I may need to do a little bit of finagling, but I could use distributive property, and then I get 6x minus 6, and this is in that format. This is linear. So we got 6x minus 6. I know it says plus b here, but really that's just the same as plus negative 6. So b is negative 6. All right, once again, we've got the x squared, similar to the square root of x. That just kills it for us. We're not going to be able to get rid of that square. So this is nonlinear. Okay, so here we're going to look at some representations of a function. Okay, we could be using words. Now, words are basically just going to describe what happens to the input to get an output. In this situation, the output is 3 more than the input. So whatever your input, add a 3. As an equation, that's what we're showing. X is the input, we're adding a 3 to it, and that tells us what the output y is. And that's all equations are. They tell you what things you have to do to your input, x, to get the output, y. Okay? In a graph, it's linking inputs with outputs. So when an x is a 0, we see that y is 3. So if the input is 0, we add a 3 to it, get the output of 3. If x, the input is 1, the output would be 4. We did a 1 plus 3 is 4. So this is a graph that shows all possible input-output combinations. You could also do something similar to that with a table. Now, a table doesn't show every single possible combinations. In this case, it just shows 4 particular ones. If the input is -1, the output is 2. We added a 3 to the input to get to the output. Mapping diagram is very similar to the input-output table. The big difference is we use arrows to draw from the input to the output. All right, discrete and continuous. A discrete domain is a set of input values that consist of only certain numbers in the interval. So what we mean by that is not all numbers are going to work. If I'm talking about going out and buying basketballs, I would never buy 3/4 of a basketball. That doesn't make sense, and they're not going to sell it to me that way. So if I have an equation that is modeling the cost of basketballs, I'm not going to use all possible numbers. I'm only going to use whole numbers, whole positive numbers. So that would have a discrete domain because only whole positive numbers make sense. Decimals, fractions, none of those make sense. I wouldn't use them, so I would only use discrete numbers. Okay, and you will see here in this graph, that's what it shows. We can have 1, we can have 2, we can have 3, we can have 4, we can have 5, but we're not getting any of this space in between. Notice none of the space in between is highlighted. So they just gave us integers from 1 to 5. In a continuous domain, it could be any number. Okay, if we switch from talking about basketballs to talking about gallons of water, I can have half a gallon of water. I can have 3/4 of a gallon of water. I can have 0.5678823 gallons of water. All of these are within the realms of possibilities. And so in that type of situation, I would use a continuous graph. Notice how it models with, we've still got a dot at 1, still got a dot at 5, but now it shows with this shading that it can be all of those numbers, every single decimal, every number that exists between the 1 and the 5. And that's what we mean by continuous. All right, so let's look at how do we graph discrete data functions. Okay, so we got this linear function, y is equal to 15.95x, which is going to represent the cost, y, in dollars, of x tickets to the museum. So each customer can buy a maximum of 4 tickets. So first thing we want to do is find the domain of the function and identify if it's discrete or continuous. Now, the domain is going to be our x variable, all the values of the x variable. So what are the possible combinations? Well, first, because it's tickets, we just think, can I buy half a ticket? Well, no, that makes no sense. So it's going to be discrete. What are the different numbers I can use? Well, I can buy 0 tickets, I can buy 1, I can buy 2, I can buy 3, I can buy 4, but it also says I can't buy more than 4 tickets. So those are all the numbers. That is the complete domain. It is all the numbers that work in this problem. Okay, next, we're going to graph the function using that domain. So one thing I do is I create this special input-output table. So I've got my inputs for x. Notice these inputs match perfectly the domain that I discovered from before, 0, 1, 2, 3, 4. Then I put them into the function, which told me what I do with all the inputs. Whatever the input is, I multiply it by 15.95. And that's what's being shown right here in the second column. In my third column, I'm finding all the output values. So 0, 15.95, 31.9. In the fourth column, I am creating my coordinate pair, which puts the input number with the output number. So 0, 0, 1 and 15.95, 2 and 31.9. Now that I've got this final column, the fourth column is the main thing we were looking for. That is all the points we want to put on the graph. So now we've got our graph. We're going to start graphing those points. 0, 0, 1 and 15.95, 2 and 31.9. Okay, now that we've got all of those put in there, the big question is, do I draw a line through them? In this case, no. Remember that we said that the data is discrete, meaning it can't be any of the numbers in between the whole numbers. We couldn't have a half. If I were to draw a line between these first 2 dots, that would be me indicating that I could have 1/4 of a ticket, half of a ticket. It would give value to all those fractions, which we don't want. We can only have a value at 0. We can only have a value at 1, at 2, at 3, at 4. We've already drawn circles where values are possible and nowhere else. Okay, and that is how you graph discrete data. Okay, so let's look at graphing continuous data now. A cereal bar contains 130 calories. The number C of calories consumed is a function of the number B bars eaten. So, does this represent a linear function? All right, so once again, remember what we were talking about earlier. Could it be some fraction of it? Do all numbers make sense? So, can I eat half of a bar? Yeah, sure. And I'll get half the calories if I do so. Can I eat 2.5 bars? Sure. 3/4 of a bar. Yeah, I can do all of these. It seems like all numbers could make sense in this situation. And it's also going to have a constant rate of change, and that's what makes it linear. Every time I eat 1 bar, my calorie content goes up by 130. That's the rate of change. For every bar, I go up 130. And since that's going to remain constant here, it's linear. All right, now we'll find the domain of the function. Well, I certainly can't do negatives, so those are out. We already talked about how fractions work, so this is going to be continuous. So the domain is going to be basically all positive numbers. Okay. Now, for our graphing purposes, I can't do every single positive number. So what I'm doing instead is I'm just grabbing a few numbers, and then I'm going to use that to draw a line. You'll notice this is very similar to what we had before. I grab a bunch of inputs. This time, these aren't the only possible ones. These are just ones that I chose so that I could get enough dots to draw a line. If I ate 0 bars, I ate 0 calories. Ate 1 bar, 130 calories, 2 bars, 260 calories. Turned those numbers into coordinate pairs. Okay, now we get our graph. And we start graphing those. So 0, 1, 2, 3, 4. Now, notice that our graph cut it off at the negative numbers. We don't have negative numbers on this graph because they wouldn't really make sense in this context. And this time I am going to draw that line because I can be all of these numbers in between. I can be 2.5, 2.6, 2.8, 2.89, 432. All of these numbers that exist in between the dots are possibilities of how much of a bar I have eaten. And it can keep going up. I mean, I can certainly eat way more than 6 bars. So this line is going to go on. It would certainly have a limit. I don't know what that limit is for how many cereal bars the human body can consume. But I'm sure there's a limit, but there's no need to put that limit into this graph. Okay, I hope this helps you in your work. Good luck.